Hi, everybody. So hope you had a good lunch. So in this presentation, I will show you how we have simulated a soft closure system. Let's see if it's... Okay, so this is the outline of the presentation. We will have a quick introduction. We will see the aim of the project. Okay, sorry. We will have a quick introduction, aim of the project, numerical methodology. Then we will see how the model has been built using two softwares, as you can see, Particleworks, but also Recurdyn. We will see the results and then in the end, the conclusions, of course. Okay, so let's start from the introduction. So what is a soft closure system? Soft closure system is something you probably have in your houses. When you close the drawer, here we have a beautiful video. This is more silent, comfortable, and so the motion of the drawer is slowed down. So how is fluid dynamic related to this? Well, I didn't know before this, but essentially those devices that you can see here and also in this video here, they are more complicated than what you think. So they're quite complicated. And here on the right, you can see also an image of one of them. Those are, let's say, different components, some deformable pistons. There is liquid inside them. So again, to simulate something like this is quite challenging. And this was essentially the aim of our project. Okay, this is real, so it's a real camera, it's a real video of the system that we are going to simulate. And yeah, the system has different components. We have like a channel, which is not just a cylinder, but is like converging, striped. So again, not just a channel. There is fluid inside it, a non-Newtonian fluid. There is a piston in black that you can see. There are some discs, which are very important in the middle, in colored in brown, which are deformable. And we also have a spring. And here we can see the motion of it. As you can see, the discs are deforming. And this deformation is very important because it changes the way the fluid is flowing. The liquid is flowing inside, and so it changes the damping effect. Okay, and based on what we know, let's say the damping effect is mostly generated by the channel and how it is shaped, the fluid, and also the discs, which are the things that we want to simulate with Particleworks and Recurdyn. Okay, so this system was tested in laboratory, so we have experimental data that you can see here in the plot. Essentially, we have a starting position, an end position, and the piston is moving at a, say, constant speed of 400 milliliters per second. And based on the position, you can see here in the x-axis, we have a higher force, which is, of course, directly in the opposite direction of the piston movement. Okay, so what was the aim of the project? We decided not to simulate everything, so we started from a simpler case. The simpler case is the one you see here. So we wanted to simulate this subsystem. So for this specific position, we know that the force applied on the piston is around 90 Newton. So essentially here we are, for the simulation point of view, we are changing the reference system. So the piston will be fixed, and we will have oil injected in the opposite direction at essentially the piston velocity. Okay, so again, the aim was to calculate the fluid dynamic forces acting on the piston, especially in this subsystem. But we also want to consider the deformation of the discs, so the three discs that you see in brown here. And then, of course, we want to compare with experimental data. So two things we want to simulate, the fluid flow and the deformations, okay? And how can it be done? So we can come to the numerical methodology using two softwares. One, of course, is Particleworks for the fluid flow simulation. The other one is Recurdyn for the flexible body simulation, okay? The two softwares are working simultaneously, okay? So their interaction is, let's say, a two-way coupling interaction. So they are coupled, and for each iteration in the simulation, essentially, pressure forces on disks generated by the fluids are passed to Recurdyn. Then Recurdyn apply those forces on the free disks that you see here, and then the shape, let's say the new shape and the new position of the disk is given back to Particleworks, and then the cycle continue. Okay, so this is the way we approach this problem. And yeah, as written here, this is a quite unique approach because doing this kind of simulation with classic CFD, so a mesh-based CFD, it's very complicated and even sometimes impossible, okay? This is something for sure we have to note. Okay, so for the model building, I will talk about Particleworks, while for Recurdyn, here we have Uwe that discuss who is the expert in the for the software. So for Particleworks, the simulation is quite simple. We fill the cylinder with oil, with particles. This is silicon oil, is a non-Newtonian fluid, so we have to implement the cross model related to the viscosity, but honestly, this is quite simple in Particleworks. And then we place an inflow on the right, two open boundaries on the left, so the fluid is able to flow. And then, of course, we have some limitations regarding the particle size due to the small gap that you see up there. So we have to use very small particles, 0.04 millimeters. So very small time step. And if you're interested in, for the surface tension model, we use CSF, pressure and viscosity model, both implicit. And okay, I finished my part, and so.
Thank you, Riccardo, for this introduction, and I will give it back to you in some slides later. No worries. Okay, yeah, the Recurdyn part, at first we have to think about what kind of simulation tasks we have or what kind of methods we need to simulate it. It was just named by Riccardo, so at first we need the Particleworks for the fluid simulation. That's, I think, the most important part here. So all the fluid interaction is done by this fluid simulation with Particleworks. The next is the multi-body dynamics for the movement of rigid bodies and also for all the springs, forces, constraints, and so on. And last but not least, we need some finite element stuff to get a reasonable deformation of these three parts, of the three brown parts. And this second and third part will be done by Recurdyn, and I will focus on the next slides just on these two parts, and then we will come back to the co-simulation. Yeah, but first of all, Recurdyn, we talk about Recurdyn. What is Recurdyn? Recurdyn is a multi-body simulation tool. It's a specialized not just for rigid bodies, also for flexible bodies, forces, friction, all this contact stuff and so on are included. And why is it so effective? We have an implicit solver algorithm inside. So that means for stiff systems, it's quite well. And stiff in this case means we have a small excitation and get a big effect. Yeah, so this is for solvers not easy to find a solution. And another one is a recursive method. This means that we have the possibility to deal with a lot of degrees of freedom. You can imagine we need this for this flexible stuff. We get a lot of degrees of freedom inside of the model, so that's why we need a powerful solver algorithm. And this recursive dynamics is also the name giving for Recurdyn, so that's why we set it from these two parts. Yeah, the solver in the background can deal with very different kinds of degrees of freedom. At first of all, multi-body systems, so we have 6 degrees of freedom for each part, and all these degrees of freedom we can fix by constraints, either one or all, it depends on the behavior. And for the deformation, we need, of course, some finite element stuff. And here we have two methods. The first is the modal reduction. This is a very smart method where we need just the methods that we have a modal analysis. And on this mode shapes based, we have a stiffness. So we get a new stiff matrix, damping matrix, and mass matrix just based on the mode shapes of the body. The good point is there are not too much degrees of freedom coming in the system, so it's quite fast. The bad point, of course, we have to pay a price for that, is that we have just linear deformations. It's a linearization around the working point. And if we have a large deformation and nonlinear, this is not possible with this approach. That's why we have the second one. This is a nodal approach. And here we have all the degrees of freedom which we have from a meshed structure inside. And there are no limitations even for nonlinear material and nonlinear deformations. We also can add some control systems, and all these different degrees of freedom will find a solution in one solving system. So there's no co-simulation in Recurdyn. There's just one solver for the solution of all the equation systems in one step, let's say. Okay, how to continue? How can we start to build up the model? So at first we need some geometry. This is usually coming from CAD. We have standard interfaces like step, parasolid, IGES, ideas, whatever you have. And after importing this, we get automatically mass and inertias based on the volume of these structures, and also, of course, of the density or whatever you give as a material property from CAD. But if we simulate this, it will just fall down, so we have to connect it somehow, and we do this with the typical constraints, contacts, forces, and so on, what we have in a multi-body system. And now we have the chance to make a first simulation just to see if the behavior without the fluid is quite well or not. If not, we have to approve it. If it is well, then we can go to the next step, and we define so-called walls. So that means all the surfaces which come in contact with the fluid, we have to define before, and they will be triangulated by Recurdyn and exported to Particleworks. And Particleworks is exactly using these surfaces for the contact between the balls and the surface. So this is a rigid body. The flexible body is quite similar. We also based our here on the CAD geometry. And at first we have to define what kind of elements we want to use, what is the size of the elements. In the next step, we have to define the material. And here you see we have also different approaches for linear, for nonlinear, plasticity, and all this stuff. In this case, we use this hyperelastic stuff. So this gives the best solution for this deformation. We will see some slides later. And we have also to take into account the damping effect of the material. So this is not a physical damping, it's a material damping, because this is not a typical finite element approach with a quasi-static solution, it's a dynamic solution. And for dynamic solution, a velocity depending force is the damping, so we have to take this into account. But these are all material parameters, and we also can include thermal effects, but this we didn't use here for our project, so I think the furniture should be in the same temperature and not heating. Okay, now we have all the ingredients to start our co-simulation. And with this co-simulation, it's explained a little bit by Riccardo. A simple example is we have some kind of vessel, put some water or whatever, some fluid inside, and connect this by a spring damper system. So then we have all the typical degrees of freedom inside. And if we start, so let's say the start point always gives a Recurdyn. Why? Because we need an initial position and an initial velocity. This information we give to Particleworks. Particleworks calculates the pressure and the forces acting on the surfaces and give this information back to Recurdyn. And then we close the circle and do this again and again until we reach the end of the simulation. And here's a typical example. I changed the spring damper system by a flexible structure. This is a full flex beam, and we fill the fluid inside, and you can see the reaction. So it's not a one-way, it's a two-way simulation of this stuff. Yeah, the next step is to come back to our application example, to our soft closure system. And yeah, now we have everything we need. We have a rigid body system. we have a flexible body system, and here we can also make a simulation first just with the flexible bodies to see if the deformation is fine or not. So a validation is always necessary, not just for Particleworks, also for Recurdyn, of course. And we defined also the flexible bodies here as walls, so that we have also the possibility to have contact between the particles and the walls, and of course between the one wall to the other. So all these contacts are available, and then we press the start button and the co-simulation starts, and here you can see the results of that. So on the left side you see just the Recurdyn model. I hide it, the bolts, the spheres, and so you can see exactly how it is deforming. And on the other side you can see the typical flow results of Particleworks, and the diagram shows the force feedback to keep this system on the position, how many force we need. And this fits maybe very well, but more from your side.
Yeah, thanks, Uwe. Yes, just to conclude, I have a couple of slides with the results. So let's move on. Yeah, so this is a video. Of course, the liquid is flowing, so we are not seeing it since everything is filled, but we can probably appreciate the deformation of the discs. It happened quite fast. So if you missed it, we have better visualization. You can see they are moving, and the fact is that once they are moving, you see those holes, the fluid flow is different, and this is very important for the forces. And in this video, we can see here on the bottom, it's the plot of again the forces acting on the piston, and in blue you have the free discs, and you can see when the discs start deforming, then also force is rising. So the forces rise, and yeah, and at a certain point they stabilize in very small interval of time, 0.015 seconds. And if we compare these results, which is the simulation result is around 110 Newton, with the experimental results, 90 Newton, it's not perfect, but we are in the good range, and especially for this kind of application, which is, again, very complicated, I would say it's, yeah, it's, let's say, a small win for us. And in conclusion, so again, we have been able to simulate a soft closure system using this unique coupling approach with Particleworks and Recurdyn to simulating the fluid deformation all together. And as we have seen, we reached a good match, around 20%. We're accurate around 20%. So we're pretty happy for this. So thank you. Thank you.